Hello everyone, welcome to my channel. This is a channel dedicated toward educational topics. Generally, we look at important theories of everything that you might might have missed or you might not be aware of. And today is our 319th video on Dewey B. Larson's reciprocal system of theory. The reciprocal system of theory is a theory of everything that, allows you to, once you know the rules of the system, you can apply the system to any subject that you like. Not easy, but something that Mr. Larson shows how you can do it. And some of his followers have done the same. Larson lived in the U.S. in the 20th century, and in the late 1950s, he came out with his two fundamental postulates, from which he ended up deducing an entire theoretical universe, and then he wrote his books based on that theoretical universe. The basic idea is that we here in this universe, we live in a universe made entirely of motion. And for Larson, motion was the relationship between space and time. In fact, when Larson first put out his fundamental postulates in the late 50s, he actually used the term space-time instead of motion. He eventually changed that to motion. And late in his life, he died in 1990, he also used the idea of just, instead of motion, of just change in 3 dimensions. So that gives you just an idea of the kind of the scope of this idea of motion, space-time. But motion was the relationship between space and time. Space and time are reciprocals of each other. They don't have any independent existence in and of themselves. They only exist together in motion. And basically, motion is a fraction with time or space as the numerator and space or time as the denominator. There are numerous different kinds of motion, and each one of them has kind of a different time-space, time-space configuration. So, for example, speed, which is the most basic motion that most of us can think of, is space divided by time. The bicycle is moving 20 miles per hour. 20 miles of space in 1 hour of time. Space over time. But then we also have, for example, acceleration. Acceleration, I dropped the ball out the window and it fell at 9.8 meters per second squared. 9.8 meters of space and 1 second squared of time. So space over time to the second power is acceleration. These are the most obvious ones, but then all of our other scientific phenomena also are relationships between space and time, fractions, such as matter itself. Matter is time to the 3rd power over space to the 3rd power. Pressure is time over space to the 4th power. Energy is time over space. And that reveals a little bit more about pressure as well. Because if you have matter, if you have energy is time over space, you could think of that as, it took me 2 hours to move that pile 25 feet. That is time divided by space. And if you have pressure is time divided by space to the fourth power, you can also then conceive of pressure as energy per volume, as volume is space to the third power. So pressure can be conceived of as energy per volume. And then you could also put in the idea of force. Force is the conjugate of acceleration. Force is time over space to the second power. And then you could also then think of pressure as force per area, because area is space to the second power. So pressure would also, not only would it be energy per volume, but it would also be force per area. And then I suppose you could also say that force would be energy per space. So anyway, you can play around with those once you kind of know those general configurations and come up with kind of relevant ways of thinking of different ones of these quantities. Now, Larson's first postulate, basically says the universe is made out of motion. Motion is the relationship between space and time. Space and time both come in 3 dimensions: coordinate space and coordinate time. Space and time also come in progressing units, or what Larson calls clock space and clock time. That means the clock is always getting later and later and later. Time is always progressing. It's always flowing. It's getting later and later and later. This is a scalar motion, a motion that has a magnitude, but it has no specific direction, like a clock. And then you also have what is known as clock space. Clock space basically means that space is getting farther and farther and farther apart. And you would envision this using a balloon with dots on it. An expanding balloon. The balloon, as you blow up the balloon, all the dots are moving away from each other, but in no specific direction. This is an outward scalar motion that is the progression of space, or the flow of space. Larson also points out that you, instead of using the expanding balloon, if you want to fill in that third dimension, he uses what you would, he says a rubber ball. You could also use something like raisin bread, where when you put the bread in the oven, all of the raisins, when the bread expands, all of the raisins move away from each other. And then space and time also have their quantized aspects. They come only in discrete units. There's a minimum unit of space and a minimum unit of time. If you don't have a full unit of space, then you do not have space. So too with time. So you have to have that full minimum unit. A minimum unit of space is approximately 4.56 times 10 to the minus 8 meters. And a minimum unit of time is 1.52 times 10 to the minus 16 seconds. So it's an instantaneous kind of thing, but that is 1 unit of time. You can fit 6 quadrillion of them into 1 second. And if you have exactly 1 unit of space and you have exactly 1 unit of time, then you have the speed of light. So the speed of light is 1 over 1 equals 1. Unit speed is what Larson calls it. And Larson refers to this outward movement at the speed of light as the progression of the natural reference system. We just went through a paper that he called reference systems, and the whereas in legacy science the stationary the reference system is stationary. We measure all our motions from zero. The car is moving 20 miles per hour, 20 miles from zero. But in Larson's system, the measurements are made from the speed of light outward in all directions. So Larson refers to that usually as space displacement. That is the amount that you are moving that is displaced from that original motion outward at the speed of light. So in the universe of motion, you have motion that precedes everything else. So the state of rest of a universe of motion is a motion outward at the speed of light. That is the state of rest. Okay, so that would be the origin or the 0 point or the ether or the reference system is the speed of light outward in all directions. And you measure your motions from that. And so that basically means that half of the universe is moving faster than the speed of light, and then half is moving slower. Larson refers to this as the cosmic sector and the material sector, respectively. And this also shows that in the Einsteinian world, the world the legacy science folks follow, they only recognize the material sector and not the cosmic sector, where Einstein says that the speed of light is the maximum speed of the universe. He is neglecting an entire half of the universe that Larson refers to as the cosmic sector. But even with our utter ignorance of the cosmic sector, we can quickly make up the difference because of the reciprocal nature of space and time. Where in the material sector, exactly what's going on in the material sector is the same as what's going on in the cosmic sector, except that you have to invert the roles of space and time. So, for example, in the material sector, you have coordinate space, 3 dimensions of space, and you have clock time. The time is always getting later and later and later. In the cosmic sector, you have coordinate time, 3 dimensions of time, and you have clock space. Space is always getting later and later and later. And so that is where, you start with your phenomena in the cosmic sector. In the material sector, you have also a sub-region that he refers to as the time region. And this is the region where you don't have a full unit of space. Remember, if you don't have a full unit, a full quantum of space, then you do not have space. And if you do not have space, that means that you have time, because the universe is made out of space and time, or the universe is made out of motion. And so it has to be space or time or both. And if it's not space, then it has to be time. So that refers to the time region. This is the region of action of less than 1 unit of space, meaning that it refers to microscopic phenomena such as atoms and particles and molecules. And in the cosmic sector, you have a small region that is referred to as the space region. And that is when you don't have a full unit of time. If you don't have a full unit of time, then you only have space. And the space region is the region of action of instantaneous particles, where you have cosmic atoms and cosmic particles and cosmic molecules. And legacy science refers to these things as antimatter, mesons. Okay, now that just gives you kind of an extended background on the reciprocal system. Today we're reading an important paper that Larson put down called the interregional ratio. And the interregional ratio is a really difficult concept for a lot of people to grasp. But the basic gist of it, in my mind, is that the interregional ratio is the statistical probability. You could also use potentiality, probability, eigenstate, and it basically is what you lose in the translation when you take your measurements into a different region of the universe. So, we just talked about these 4 regions divided by 3 boundaries. There's the unit space boundary, there's the unit speed boundary, and then there's the unit time boundary. The unit speed boundary divides between the material sector and the cosmic sector. The unit space boundary then divides off this time region from the rest of the material sector. And the unit time boundary, or the space region, divides off the space region from the rest of the cosmic sector. So you really have 3 boundaries and 4 regions. We generally reside in the material sector, the macro area of the material sector. So when we want to make a measurement into the time region, or we want to make a measurement into the space-time region, which is the half of the cosmic sector, the macro half of the cosmic sector, or the macro portion of the cosmic sector, what we observe is not the full picture. What we observe is just a small percentage of, or a ratio of, what is actually going on. So we have to take what we observe and multiply it by the interregional ratio to get the actual picture of what's going on. So he's about to explain that process. So the interregional ratio ends up being very fundamental into making measurements, especially when you look at maybe like his book, The Basic Properties of Matter. When you're determining things like the interatomic distance, or when you're determining things like the atomic weight of particles, you're using the interregional ratio in all of those determinations. And the interregional ratio varies depending upon whether you're applying it to an atom, or whether you're applying it to a subatomic particle, or whether you're applying it to a photon. These are different interregional ratios, and he kind of derives those things in this paper here. Okay, so at the this is how it starts, the interregional ratio. At the 1984 ISIS conference in Salt Lake City, a discussion of the interregional ratio concluded with an understanding that each of those concerned should write a statement of his ideas on the subject for publication in Reciprocity, which Reciprocity is the journal that was dedicated to the pursuit of the understanding of the reciprocal system. What follows is Dewey B. Larson's contribution to that. Okay, so the first point that should be noted in connection with this ratio is that it is a basic physical constant, like the gas constant, the gravitational constant, etc. Conventional physical theory has no explanation for any of these constants. It simply uses the measured values without attempting to explain where they come from, or what they mean, or even if they have any meaning. So this is an important point to just make, because it again applies to really about the history of science. People, so-called skeptical scientific people, they generally, when they look at the reciprocal system, they try to pick it apart with every ounce of their being. And so where's he coming up with that reciprocal? Where's he coming up with that interregional ratio? He's not even explaining where it comes from. But at the same time, they've just accepted the gravitational constant and the gas constant without any questioning whatsoever. Even though they stand in the same they have the same standing. They are constants, and none of them have any type of explanation backing them up. But now Larson is actually going to provide the explanation for the interregional ratio, but there still isn't going to be any type of explanation for the gas constant or the gravitational constant. But these skeptical scientists out there are, busy wasting their time poking holes in Larson's theory, but they can't turn the mirror on themselves and apply the same standard upon their own theories. Okay, if anyone has difficulty in following the theoretical derivation of the interregional ratio, I would suggest following this prevailing scientific practice for the present and accepting this ratio as a measured value, leaving its theoretical status to be considered later, after more familiarity with the theory has been gained. But I am going to provide the theoretical basis for it here. But if that's too much for you, just accept it as is, and we'll figure it out later. This ratio can, of course, be measured in the same way that the other fundamental constants are measured. That is, by applying one of the relations in which it participates. This is how I obtained it originally. I measured it and used it in my studies long before I formulated the reciprocal system of theory, and found a theoretical explanation for the measured value. In order to appreciate the significance of the ratio, it is necessary to have a reasonably good understanding of the basic features of scalar motion. Now, just recall that earlier this week, within the last 7 days or so, I went through a paper that Larson wrote that is called Scalar Motion. So if you want to go back about a handful of days, I think that paper went on for about 4 days. And so you can learn all of the basic features of scalar motion from that paper. But basically, scalar motion is a motion that has a magnitude, but it has no specific direction. And scalar motion is something that is recognized by scientists, but until Larson came around, it was not recognized in its significance. It was seen as kind of an anomalous, random outlier in regular scientific theory. Larson put it toward the center of his universe of motion. The existence of this type of motion is not recognized by conventional science, but there is an obvious oversight as scalar motion can be observed. For instance, we find that the distant galaxies are all moving radially outward away from our own galaxy. Since we cannot justify assuming that our galaxy is the only stationary object in the universe, we have to conclude that we are likewise moving away from all of the other galaxies. That is, we are moving outward in all directions. A motion in all directions is a motion with no specific direction. That's the motion of the galaxies. Thus, the motion of the galaxies is scalar. From the postulates of the reciprocal system of theory, we find that the basic motions of the universe are scalar, simply relations between space magnitudes and time magnitudes. Once we have recognized that motion of this nature actually does exist, even though conventional science does not recognize it as such, the postulate that this kind of motion, the simplest form of motion, is the fundamental entity is entirely logical. Of course, fundamental postulates have to be justified by their consequences, but it helps to know that they are soundly based. In a three-dimensional universe of motion, there are necessarily three dimensions of motion. That is what the adjective three-dimensional means. But only one dimension of motion can be represented in the three dimensions of space portrayed by the conventional reference system. Any motion in this reference system can be represented by a vector, and a combination of any number of such motions is a one-dimensional motion represented by the vector sum. In order to grasp the significance of the expression three dimensions of motion, the term dimensions has to be interpreted in a mathematical sense. That is, the foregoing expression refers to a motion that requires three independent quantities for a collective definition. To distinguish these dimensions of motion from the dimensions of space or of time that can be represented in the conventional three-dimensional reference system, I am calling them scalar dimensions. Okay, so this is the the key thing is, and he went through this in his paper on scalar motion also, is that in order to represent a one-dimensional scalar motion, you need three dimensions of space. So that's your whole coordinate system. Your Euclidean coordinate system is required just to represent one scalar dimension. And there are three scalar dimensions, which means that the other two scalar dimensions are outside of the realm of your reference system. They cannot be represented by a three-dimensional coordinate Cartesian Euclidean reference system. So that shows you the limitations of our kind of geometrical representation. Scalar motion is not geometrical, it is mathematic. You only have magnitudes, you do not have directions. And so scalar motion is represented by magnitudes. And our reference system is limited. And so you can use different reference systems to represent different things. Larson uses what he calls the natural reference system, and he says that is the reference system that the universe actually conforms to. That is, the 0 point, the reference point, is motion outward at the speed of light. But the conventional scientists use your stationary reference system, where the 0 point is zero motion from wherever it is that you're measuring. And you get different results depending on what reference frame you're using. And you can also you can measure from not only from zero space, but you can also reference from zero time. So those are fundamental points. But so he's basically attempting to construct a system that can compensate for the fact that the reference system is not giving us the full picture. And that's where a lot of this interregional ratio comes in. We will resume this paper and finish this paper tomorrow. And again, if the derivation escapes you, don't worry about it. Just hang in there and just accept it as is, and then you can ask questions later. That's the key to learning the reciprocal system, is that sometimes things aren't going to make complete sense because you just don't have enough of the picture, and you're too invested. We are all too invested in the old paradigms. And so there's a lot of unlearning that needs to be done. And we're always trying to fit all the new concepts into the old concepts. But in some cases, the new concepts overrule the old concepts, and we have to set aside the old concepts. And so, in terms of the reciprocal system, it requires that we suspend disbelief just for a little while, enough to become accustomed to the system, and then we can weigh it out on its merits, and give it a fair hearing. But we can't really give it a fair hearing if we're already invested in these old paradigms. So that is my advice about learning the reciprocal system, and hope you follow that. I hope you at least take it seriously, and thank you for tuning in today. Have a great night.